Hello again, gentlemen. This is Mr. Theodore coming back with part 2 of 2 in our series of videos about solving systems of equations. Yesterday you watched a video in which we described how we can solve a system of equations by graphing, either using paper and pencil or using our graphing calculator to generate the graph for us. Today we're going to be looking at similar systems of equations, however we're going to be solving them algebraically. So we won't need to draw any graphs. We're going to use the numbers and variables in the equation to allow us to solve for the solution of the system, which in review was the point of intersection of our two graphs, also known as the point that simultaneously works in both equations of our system. So we're going to look at two methods of solving a system algebraically today. Those two methods are substitution and elimination, and we'll talk about what it will look like if your system has infinite solutions or no solutions. If we're solving algebraically. So first of all, let's dive a little deeper into the two methods of solving. Substitution is a method in which you're going to use the value of one variable in one of your two equations of your system to solve the other variable. Right? You're going to use substitution to eliminate one of the variables so that there's only one variable left, and you can then solve for that one variable. Elimination, on the other hand, is a process in which you're not going to use substitution. Instead, you're going to get an opposite for your coefficients and add your equations together, but still with the purpose of eliminating one of your variables so that there's only one left, and you can therefore solve for the value of that one variable that's left. So it's really important that you understand there's a lot of similarities between both methods. Really, the only difference is how you choose to eliminate your first variable. So let's look at why it's important for you to eliminate one variable from the equations in your system to allow you to solve for the solution set of a system of equations. Yesterday, and in chapter 2 as well, we talked about how many solutions a linear equation in two variables have. And we said because of the two variables, there's an infinite number of solutions. Any point on the graph is a solution of the equation. There's an infinite number of points on the graph as characterized by the arrows that we draw on the ends of each line. So two variables, infinitely many possible solutions. However, if we're able to eliminate one of those variables, now we narrow down the number of possible solutions. If I were to say eliminate the y variable from this first equation here, and only have one variable left, just the x variable, I would be able to solve for the exact value of that x variable without any variation. Right? Now there's not infinite solutions, there's only one solution. And so that's what these two algebraic methods of solving seek to do. They seek to take a system that has two equations and two variables and to eliminate one variable from your system so that there's only one variable left, and you can then solve for the exact value of that one variable. Let's look at the two methods now. First of all, substitution. Substitution is a process where I'm going to take my original system and I'm going to look at either of the equations in that original system, and the first thing I'm going to do is solve for the value of one of the variables. So when I look at this original system, I notice the bottom equation has a y variable with just a 1 as its coefficient, which means it'll be pretty easy for me to solve for y in that bottom equation. I can just add 3x to both sides, and then I can have my equation written in y equals form. So now that I know what y equals in the bottom equation of my system, I'm going to use what y equals in the bottom equation of my system to solve the top equation of my system. And the way I'm going to do it is I'm going to take the value of y from my bottom equation and I'm going to plug it into the top equation for the y variable, in effect eliminating that y variable so that there's only a x variable remaining. So when I substitute the value of y into the top equation, I end up with 2x plus 3 times the quantity 3x minus 7 equals 12. Effectively taking an equation that started with two variables originally and eliminating one of those variables. So that my next step would then be to solve for the value of that one remaining variable. And once I have the value of that one remaining variable, I can substitute that value back into either equation of the system. Remember, the answer that we're going to find here should be a solution of both equations in the system. So it doesn't matter which of the two original equations I plug my value of x back into. And once I substitute x out there, I only have one variable remaining again, but this time that variable is y. So I can solve for that variable. And once I then have the value of y, I know the full solution of this system, or the ordered pair that is a solution of both equations in the original system. For this particular example, that solution is the ordered pair of 3, 2. And I always want to check that solution by plugging each of those values, the x and y coordinates, from my solution back into the two equations of my original system and verifying that what I think my answer is actually works as a solution of both equations. So next, let's look at elimination. Elimination is a similar process, but with elimination, we're not going to substitute out our first variable. What we're going to do is we're going to take our original system and we're going to use simple algebra principles of multiplying to rewrite one or both of our equations so that one of our variables has opposite coefficients. So when I look at my original system, I notice that the top equation has positive 3y and the bottom equation has positive 1y. Right, positive 3 and positive 1 being those coefficients. And I notice that if I were to multiply everything in that bottom equation by negative 3, that would create an opposite for the y variables. Because if I multiply everything in that bottom equation by negative 3, that would make my bottom equation 9x minus 3y equals positive 21. And again, why is that important? Well, now when I look at my y variables, I've got positive 3 as the coefficient for the top equation and negative 3 as the y coefficient for the bottom equation. So those two coefficients are opposites. And once I've got an opposite, the elimination method eliminates one of the two variables by adding them together. And since I'm adding opposites together, they'll cancel each other out. And so I'll be left with only one variable. And from here, I can solve for that one variable and substitute it back into either of the original equations to solve for the value of the second equation, just like I did with substitution. So if we look at these two methods side by side, you'll notice the only difference between these two methods is in how you eliminate your first variable. Once that first variable has been eliminated by either substitution or by getting an opposite and adding the equations together to eliminate one variable, the process is the same. In both cases, I ended up with 11x equals 33. And so once I solve for that one variable, for either method then, I'm going to substitute the value of the first variable into either of the two original equations in my system and solve from there. So the final thing I'd like to take a look at today is what is it going to look like when you solve a system that has infinite solutions or no solutions algebraically. Yesterday you looked at some systems with infinite solutions and no solutions graphically, and it was very easy to determine whether they were infinite solutions or no solutions graphically. While when we were solving a system by graphing that had infinite solutions, the lines coincided. They lied on top of each other, and we could visually see that they were the same line. When we solved a system of equations that had no solutions graphically, we could visually see that the lines were parallel, and we were able to use the slopes to verify that they were indeed exactly parallel lines. When we're solving a system algebraically, we don't have the advantage of having a visual representation of the equations. And so it's a little bit more difficult for you to determine whether the lines actually coincide or are parallel. So what's going to happen is, in the process of solving using either of the two methods of solving algebraically, if your system has infinite solutions or no solutions, all of your variables will cancel out. And so what you're going to be looking at is, do the numbers remaining make a true statement or a false statement? First of all, let's talk about why all the variables might cancel out. In an equation that has infinite solutions, we know that the two equations must be equivalent. And if we don't happen to see that before we go through the process of solving, you'll notice that if I use substitution here, when I solve for the value of x in my top equation, and I use that to substitute into the bottom equation to eliminate the x variable, all of my variables cancel out. Well, why did all the variables cancel out? It was because they were the same to begin with, meaning the slopes were the same. And so that was the fact that the variables canceled out was an indication that the slopes were the same. And so the numbers that are remaining verify for me whether or not the y-intercepts were the same. So if those numbers are equal, then the y-intercepts were the same, and that means the lines were exactly the same, and therefore there's infinite solutions. Versus if there's no solution, all the variables are going to cancel out as well, because again, when all the variables cancel out, what that signifies for us is that the slopes are the same, which could be an indication that the lines are parallel, but only if the y-intercepts are different. And because the y-intercepts are different, once all the variables cancel out, the numbers that are remaining make a false statement. Right? So the false statement signifies that the y-intercepts were different, and because the variables all canceled out, I knew the slopes were the same. And any system where the slopes are the same but the y-intercepts are different will have no solution. So the fact that I got 0 equals 4 when I solved this system by addition verified for me that the slopes were the same but the y-intercepts were different, and therefore I would have no solution. So hopefully, gentlemen, I hope this video has helped you to identify the two methods that you could use to solve a system algebraically and some of the similarities and differences between those two methods. And in addition, I hope that you have an understanding of what it will look like when your system has infinite solutions or no solutions when we solve it algebraically as a result of watching this video.